Now, one is the graphical method that I have shown here, how the rate of reaction become double to triple. Another mathematical expression to explain that rate of reaction become double to triple. Now, Arrhenius gave an equation that is K is equal to A e to the power minus EA upon RT, where K is the rate constant. This K is the rate constant. A is Arrhenius factor. Chitransh, yes, it is the topic of Arrhenius concept. But Arrhenius concept not of the acid and base. It is the concept of activation energy. Right? Arrhenius constant. And EA is the activation energy. And T is the temperature. Taking logarithm both sides, I can say taking logarithm log of n, natural log of K is equal to natural log of A minus EA upon RT. This is the graph at T1 temperature, so the K1 is there. At temperature T2, log of K2 is equal to logarithm of A minus EA upon RT2. Right? Subtracting the second equation from the first, we get natural log of K1 minus natural log of K2 is equal to minus EA upon RT2 minus EA upon RT1. It is equal to now K1 upon K2. Make it like this. 2 minus 1. Please make changes here. Please make changes here. Make it 2 minus 1. Just a minute. So natural log of K2 minus natural log of K1 is equal to minus EA upon RT2 minus EA upon RT1. So it is equal to K2 upon K1 is equal to EA upon R 1 upon T1 minus 1 upon T2. Converting to the log to the base 10, we can say 2.303 log to the base 10 K2 upon K1 is equal to EA upon R 1 upon T1 minus 1 upon T2. I hope you can solve this question. You can just simply solve this. Are you getting me? Yeah. So from this we say logarithm of K2 upon K1. Now I'm coming to the main core chemistry that I left here as a mathematician. I was in the mathematics part, but now I come into the chemistry part of it. I can, yeah, EA, it is a 1 upon T1 minus 1 upon T2. This is what we can get here. Now, if you make the difference of a T1 and T2 by 10 degrees Celsius, suppose a reaction T1 is 298 and the rate constant is K1, and T2 at T2 it is the K2, let it be at 308 Kelvin. Right? We have to find the value of the we can have to find the ratio of the K2 upon K1. For every reaction K2 upon K1, I can say this is temperature coefficient theta. This ratio theta lies between 2 and 3 for every reaction. For every 10-degree rise in temperature, rate becomes double to triple. Are you getting me? So this is a mathematical proof of the fact that for every 10-degree rise in temperature, rate becomes double to triple. In some cases, exactly double. In some cases, more than 2. In some cases, it can go up to 3. Any doubt, students, please ask me. Which part is not clear? Yes, yes. Which part is not clear? After blue words, what is the meaning of the blue words here? This is. Now, where the chemistry starts. Mathematics, you know, right? You can solve this equation simply. Fine. So you're stuck with the chemistry part here. I say like this. Just a minute. I say at temperature T1, rate constant is K1. Is this clear? And at temperature T2, the rate constant is K2. And I keep the temperature difference T2 minus T1 is equal to 10. It means I'm getting the rate constant K1. I'm getting the rate constant K1 at temperature T1. I'm getting the rate constant K2 at temperature T2. If I keep the difference as a 10 Kelvin, if I keep the difference of 10 Kelvin, then what do you find? This K2 upon K1 lies between 2 and 3. Lies between 2 and 3. It means the rate constant becomes double to triple, and that is why the rate of reaction also becomes double to triple. Are you getting me? Yes. You mean 10 to the power RHS. I'm not getting you, Yash. I'm not getting you. So I say this is theta value that become double to triple. Difference between T1 T2 is not 10. Okay, right now we are discussing about that if the temperature difference is 10, the rate become double to triple. If the temperature difference is 10 only, then the rate of reaction become double to triple. We have proved this thing only. Are you getting me, Yash? Our question was that for every 10-degree rise in temperature, rate of reaction becomes double to triple. And we have proved it by two ways. One, the graphical method. Second, by the mathematical equation. Yes, any doubt till now? No doubt? Perfect. Now, that is not required. How to find activation energy? Okay, I'm coming to it. Just see this question here. Please see this question. I'm coming to your question. Yes, Jen. The rate constant K for a decomposition is this much at 546. If activation energy is this much, what is the pre-exponential factor? Pre-exponential factor is the A value or RNS constant. I hope you have to just put the values and you can solve it. Just put the value of the rate constant, just put the value of the activation energy and temperature and just solve it. Yes or no? Pre-exponential power, pre-exponential means basically I gave you this equation K A e to the power minus EA upon RT. This is the exponential. E is exponential. Pre-exponential means A. Pre-exponential is A. It is also called as Arrhenius constant. It is also called as exponential constant. So you can solve this part, right? And now, if the question goes like this, is the rate of reaction quadruples. Quadruples means 4 times. It means I can say K2 upon K1 is equal to 4. When a temperature difference is 20 Kelvin, you can say 20 Kelvin somewhere here. 20, yeah, 20 Kelvin. And activation energy, calculate activation energy here, assuming that it does not change with rise in temperature. So what should I do? I know this equation K2 upon K1 is equal to activation energy upon 2.303 or 1 upon T1 minus 1 upon T2. Getting me? This value is equal to 4. Activation energy to be calculated 2.303. R value is 8.314 joules. 1 upon 293 minus 1 upon 313. Now you can get the value of the activation energy from here. Yes, are all of you getting me? Log value. Last time I think I discussed the log without log table. I discussed the log table calculation even without log table, right? Log of 4 is 0.6020. Log of 4 is okay. Okay, I should say logarithm. Okay, I got you. I'm sorry. Is that clear? Right. Last time I also gave you how to get the value, the log value, right? Without any even without a log table. That's it. How we have to calculate. Now, basically on this same topic, we can discuss number of questions here, right? Let us see this question now. The rate constant K for the decomposition of H2O2 is given by this value. Calculate activation energy and at what temperature its half-life time will be 256, right? It means from the half-life time, I can get the value, the rate constant K. Getting me? Tell me the formula by which I can get the value, the rate constant K from a half-life time. Yes. Half-life time, rate constant K is equal to 0.693 upon T half. So K can be calculated, right? What is A here? What is A here? Is 14.3, right? 1.25. That's a simple, put the values and you can get the value of the activation energy. I hope you're getting me, right? Okay. Rest is all value substitution and calculation. I told you what is temperature coefficient. Temperature coefficient is the ratio of the rate constant at two different temperatures differing by 10 Kelvin. So Kt plus 10 upon K. And this theta value lies between 2 and 3. And for every 10-degree rise in temperature, rate of reaction become double to triple. Rate of reaction become double to triple. Getting me? All of you? Right. Now, what is the effect of temperature on the activation energy? Can you tell me, will the temperature affect the activation energy? No. Yeah. It is same. It remains same for a particular reaction. Only what we do with rise in temperature, we provide the activation energy and make the reaction happen. Reaction is possible by increasing temperature. Otherwise, the activation energy remain same. Right? Are you getting me now? No. Only what happens is we cover the energy barrier by increasing temperature. Right? Leave this part. I hope it's very clear now, all of you. Leave this question. Everything is clear, students? Right. Now, I'll be discussing some important topics. Yes, yes, yes. Uh, in each question, it is mentioned that assumed temperature effect in activation energy is constant. In question, in yeah, we have to it is maybe mentioned, it may not be mentioned. Whatever, it's a fact that it is constant. Activation energy does not change. Only by with rise in temperature, we make the reaction happen because we provide that activation energy. Right? Now, leave this point. I am coming to one important aspect here. Now, I'm coming to one important question part here. That was the topic basically that we left yesterday. I discussed with you that the rate constant K is equal to, for the first order, can you tell me rate constant K value? Rate constant K for the first order, 2.303 upon time t logarithm of A naught upon A. This is the rate constant K for the first order. Yes, students. Remember this? Yes. Okay. What is A naught? What is A naught? Yes, let me know. What is A naught? Initial concentration, right? What is A? What is A? Final concentration. Means after time t, not final, but we can say after time t, what is the concentration? Okay. Now, if the reactant and the products are not in the solution form, but they are in the gaseous form. They are in the gaseous form. Then we cannot measure their concentration, but we can measure their pressure, right? We can measure their pressure. So in that case, we must put the pressure terms here. Initial pressure upon pressure at any time t. Getting me? Initial pressure upon pressure at any time t. So I'm putting this A naught upon A. Yes, students. Why not volume? Okay. Now, why not volume? I'm answering this. Suppose some gas has reacted. Will the volume of the gas change after time t? After time t, suppose some amount of reaction has taken place, some gas has reacted. Will the volume of the gas change? No, the remaining gas will occupy the same volume. That is why I'm not choosing the volume, but will the pressure change? Will the pressure change? Yes. That is why I'm choosing here the pressure, but not the volume. Right? So, are you getting me this one? I'm coming to you, Lalit, Yash. I'm answering all of your questions. So, can you write it like this way? A upon A minus X. A is the initial amount, and this is the concentration amount left after time t, A minus X, where X is reacted here. Now, suppose I have this equation. A is a solid, B is solid, C is a gas. At time t, I have A concentration of the A, but the C is 0. After time t, some amount of the X has reacted, the C formed will be equal to X. Are you getting me? So at infinite time, this will be equal to the value of A. It means initially I have P naught pressure. At time t, I have Pt pressure. At infinite, I have P naught pressure. Right? Now, from here, I can say this P infinity, that is initial pressure, upon P infinity minus Pt, that is equal to A minus X. It means instead of writing A upon A minus X, I can write here P infinity upon P infinity minus Pt. Pressure at any time t depends upon how much X is formed. I repeat here. See here. At any time t, X is the amount of the C formed. Right? All of you getting me? At any time t, X is the product formed, and corresponding to the X, there will be some pressure. At infinite time, A is the concentration, and the pressure at infinite time will depend upon the value of the A. Right? Now, I say at a pressure Pt is directly proportional to the X formed. Pressure infinite depends upon A, and P infinity minus Pt is equal to A minus X. Right? So instead of writing A upon A minus X, I'm just putting here P infinity minus Pt. Right? Uh, who is there who is saying mole fraction? Let me see. Yes, here X is not a mole fraction. It is the amount formed only. It is only the amount formed. Nothing to do with the mole fraction here. Yes, I'm not getting you. Infinity means when the reaction is carried out up to infinite time, when overall A becomes zero, means the amount of the A is now become zero. Nothing of the A has is now left. Everything has been converted into product. Right. So I can use this formula for numerical purpose instead of using the concentration. Instead of using the concentration. Am I clear? Now, I'm considering here another case now. Please focus here, another case. Here, I have two product as a gas. In the previous case, it was only one as a gas. Yes, I think you are misleading somewhere. Here, X is the amount of the product formed, but not the mole fraction. Right? Moreover, for the mole fraction, we are not using X, but we are using their special term as a chi. Yes, are you getting me? I'm not using X as a mole fraction because more for the mole fraction I should use the symbol chi. So here X is the amount of the product formed. That's it. So here in the previous case it was only one reactant, one product as a gas, and here I have a two product as a gas. See here. So at time zero, I don't have a B and C. At time t, I have an X here. At infinite time, A is not totally zero, but A formed here, right? So time t, pressure at a time t is directly proportional to 2x. Getting me? And pressure at any time t infinite is directly proportional to 2a. So P infinity minus 2 Pt is equal to 2a minus x. Right? Getting me? Okay. Now, for writing a upon a minus x, I should write here P infinite minus P infinite minus Pt. So this is the equation for the P infinite minus Pt. Any doubt till now? Let me know. No. And now here I have a question. Let us try this question. Will you try? Will you try? Okay. Take your time. 1 minute, 2 minutes. Some students are very, very late, my dear. Amay, now you are reaching. It's too late. Are you trying this question? Got stuck. Okay, let us try. Okay, student, let us try this question. If you are done partially, check it out. Phosphine decompose in the presence of inert gas. Okay. Show that the reaction is the first order. Find the rate constant K. It means if I find the rate constant at different intervals, if that comes out to be same, then this reaction is of the first order, right? This is the only concept that we know. So what we have got is at time zero, it is this. At 60 second, at 120 second, at infinite time, pressure is given to us. Now what we had done is A 0, 0. Is that clear? At time t, A minus 4x, it is x and it is 6x. Is that also clear? Everybody? Okay. Then at time t0, we have P0 and hydrogen 0. A minus 4x, x it is 6x. Or I can say in terms of the A, it is A by 4 and it is 6A by 4. Is that clear? At infinite time. At infinite time. Is that clear? Right. So I is the number of the mole of the inert gas, because that reaction taking place in inert gas also. So A plus inert gas directly proportional to P naught. See here, when time is equal to 0, the pressure should be equal to P naught. And now A plus 3x at any time t. I'm talking about the pressure at a time t. So you add all of these. And pressure at infinite time, you can add all of these. So, is that clear? Rest is all simple calculation. Rest is all simple calculation. Just see to it. Just see it. It's very simple. Only the beginning part is the chemistry. Rest is all just simple mathematics. Where you have to use the stoichiometry. See, the pressure is also due to the inert gas. The pressure is also due to the inert gas. We can't neglect the pressure of the inert gas. I hope you have seen it. Why 6A by 4? Very simple. A 0. Now, after when this phosphine becomes 0, it will be equal to 6 by 4 into A. 6 by 4 into A. Yes, Rahul, I hope you are getting me. Simple. Yes, Rahul, I'm not getting you. Then why should we not consider it in the stoichiometry? I'm not able to get your question. Okay. So inert gas. Still, I'm not getting your question, Yash. It is inert gas. Yes. So I'm not getting your question again. Okay. Uh, in the above question, in the inert question, inert gas. refers. Okay. Yes, I'm not still not getting your question. Okay. Anyways, yes, we can discuss it later. We don't stop here, right? So here I have another example. When one component can be determined by the titration. Do you know what is meant by the word titration? Yes, friends. Do you know what the word titration? No response. You know what the meaning of the word titration? Yes. Okay. I'm coming to such type of problem here. So when one component can be determined by the titration, let's understand here what is meant by the titration here. I'll make it clear, Neha. So hydrogen peroxide, hydrogen peroxide is a reducing agent and it reduces the KMnO4. What we do is we take up the potassium permanganate in the burette, right? Here we take up the potassium permanganate in the burette, and here we take up the H2O2, right? Then we drop by drop we add here the H2O2 until the color becomes colorless to the pink. The color changes from colorless to the pink. We determine the volume here. How much volume the KMnO4 is used. Are you getting me, all of you? You had done this experiment, right? Not with the H2O2, but you might have done with the Mohr salt or with the oxalic acid in your lab, right? So initially I have A and oxygen is 0. A minus X after time T and oxygen left is X by 2 and H2 is X. Is that clear? So at time 0, when time is 0, means only H2O2 is there, we have V naught value, right? After time T, some amount of the H2O2 will be consumed, right? That will be titrated by the potassium permanganate. It means the volume of the KMnO4 will be used less. More the amount of the H2O2, more the amount of the KMnO4 required. And now after time T, some amount of the H2O2 has got decomposed, so the volume of the O2 KMnO4 used will be less. Are you getting me? Getting me, students? Yes, Neha? Yes. Now, initial amount of the KMnO4 used is directly proportional to the amount of the H2O2 taken in the beginning, that is A. After time T, it is A minus X. Got it? So if I divide the two, that will give you A upon A minus X, or I can say V naught upon V. So instead of writing A upon A minus X, I can write here V naught upon T. Let me know if you find any problem here. Because basically we are writing the rate constant value, K, that is equal to 2.303 upon time T, logarithm of V naught upon V. Right? Instead of this value, A naught upon A, I'm putting here V naught upon VT. Here we are measuring the volume of the potassium permanganate. In the previous case, when it was gas, we were measuring their pressure. I hope you're getting me. Yes, friends. Yes, we can consider concentration also in some cases. Yes, you're right. We can use anything as a concentration in terms of the volume, in terms of number of moles, in terms of the pressure also, whichever we can measure. Whatever we can measure, we can take that quantity. Right, Yash? But for these experiments, when we are using the titration technique, When using a titration technique, we can measure the volume. See, volume of the KMnO4 used. But our practical technique is suggesting us that yeah, in the burette we have KMnO4. In the beaker we have hydrogen peroxide. We add drop by drop and find out what is the volume of the KMnO4 used to to get the H2O2 concentration. Everybody is clear? Yes, friends. Are you clear? Yeah, very simple one. It's not difficult. Okay. So what is rate determining step? I told you yesterday also. I think in the previous classes also I had discussed here what is meant by the term rate determining step. You tell me, then we proceed ahead. Yeah, the reaction which is the slowest in all the steps. That basically determines the speed of reaction. That is called as a rate determining step. Now, I have this example here. K1 A plus 2B to give C plus D. In the step 1, A plus B to give C plus I, and now B plus I to give D. Ended out here. And now it gives step 1 is a rate determining step. If it is given that is equal to rate determining step, then molecularity is equal to 2 for the overall reaction. I think we know what is the meaning of the molecularity, what is meant by the term order of reaction, right? What is the difference between the RDS is the rate determining step. RDS stands for rate determining step. In our previous classes, I have discussed what is the rate determining step, how to find the molecularity and how to find the order of reaction, right? The same thing they are now, the slides are being showing here. Not required right now. Just okay, what is pseudo first order reaction? We'll discuss about this very important topic left now. What is pseudo first order reaction? Understand here. Let us consider this reaction. It is basically hydrolysis of acetic acid, right? Hydrolysis of acetic acid. And if it is given that reaction is elementary, then rate should be equal to K into the concentration of the ester and the concentration of water. And if water is taken in excess as a solvent, then in this process water will not be consumed at all, or water will be consumed in very, very less quantity, right? So I can neglect that water, and now rate is equal to R dash into this value. Are you getting me till now? Yes, please. Are you getting me? Yes. What we're doing here is we had taken one reactant as in excess, when the concentration will remain same, because the water is in excess. It means even if it is small amount of it is used, that small amount will be negligible, and we can say the water remains same, the constant remains same, right? Getting me? So such type of reaction, the order is equal to 1, molecularity is equal to 1. This is called a pseudo unimolecular reaction, because otherwise water is also being used, but its amount is not changing much. That does not have a significant value of H2O2. So water, significant amount of water is not being consumed. So we say the water is amount is constant. So this is called as a pseudo unimolecular reaction. Pseudo unimolecular reaction. Are you getting me now? Till now? Any doubt? I repeat. If there's some problem also, then I can discuss that also. I take up this case here. Sugar, that is C12, H22O11. I have sugar here. I add here water, and we add here H positive ion. Now we get here C6H12O6 plus C6H12O6. This is the glucose and this is the fructose. Yeah, this is the cane sugar. The rate of reaction should be K into C12H22O11 and water. But the amount of water is taken in excess, therefore it does not depend upon this value. So it is only depending upon one molecule only. Such type of reaction is called as a pseudo-unimolecular reaction. It's called as pseudo-unimolecular reaction. Yes, all of you are getting me? It should always be water. One solvent should be in excess, not necessary water, students, not necessary water. Here the two reactions that I have shown that contains water as a solvent, but it can be any other reactant also, but that is in excess, such that its concentration is not changing at all in the overall reaction. Getting me? Leave this question. Yes, students. Any doubt till now? Yeah, glucose and fructose has same formula. They have same molecular formula but different structure formula, right? How are they so? Let us understand. Whenever I say C6H12O6, it can be glucose, it can be fructose. If it is an aldehyde group, CH3CHO, aldehyde group. I am drawing the structure here of the glucose molecule. Right? This is called as the glucose molecule. And if it is like this, 1, 2, 3, 4, 5, 6, here I have a ketone. This is the fructose. Are you getting me, all of you? Yes. Any doubt? Yes. Are you getting me? So basically glucose and fructose have same molecular formula, but they have different functional group. You can see the glucose is an aldehyde and ketone, fructose is a ketone. They have a different functional groups. They have different functional groups. One is the aldehyde, other is the ketone. Yes, friends, are you getting me? Right. So this is a pseudo unimolecular reaction. Now, if you have any doubt, you can ask me now. Otherwise, I'm coming to the next topic briefly. One little bit topic is left about the catalysis. What type of reaction is this if it is energy versus progress of reaction? Endothermic or exothermic? Endothermic or exothermic? Endothermic, good. It means if this much amount of energy is provided, then only reaction is feasible, otherwise not. If this much amount of energy is required and it is provided, then only reaction will take place. Suppose in our lab we don't have very high power energy source as required by the reaction. It means in that case we cannot perform the reaction, we cannot perform the practical. Practically we do it, but in the presence of a catalyst. What is that catalyst is, it decreases the activation energy. Now the graph is with the positive catalyst. This is without catalyst, and this is with positive catalyst. Whenever I say positive catalyst, that increases the rate of reaction by decreasing activation energy. By decreasing activation energy. Positive catalyst increases the rate of reaction by decreasing the activation energy. No, threshold energy is not decreased. You can say the threshold energy is this much only. That remains same. Yes, of course, to threshold energy also. Yes, you're right. But basically, we are providing this much amount of energy. Initially, we were providing this much amount of energy. Right? Initially, we were providing this much amount of energy. And this is the now decreased amount of energy. So positive catalyst basically increases the rate of reaction by decreasing the activation energy. Yeah, Lalit, you are right here. So both the decreases also. Am I clear? All everyone? Yes, internal energy does not change at all. You're right. But if the reaction is with the negative catalyst, let us see here. This is the reactant energy, and this is the again a product here. Suppose we have to slow down a reaction, we add a negative catalyst that increases the activation energy. This is without catalyst, and this is with negative catalyst. Negative catalyst increases the threshold energy or the activation energy, both.